Hydropneumatic tanks, or hydrotanks, are devices that are often used in drinking water systems in place of large overhead storage tanks. Hydrotanks are part of the KY pipe hydraulic model. They are defined with pressure switches, volume, and an associated pump. When we run an extended period simulation, or an analysis over time, we can see the tank cycling between its pressure switch settings. We can apply different symbols to the hydropneumatic tank and to other elements in the model. Insurance companies and regulatory agencies have become more concerned lately with the effect of power outages on hydropneumatic tanks. This graph shows the effects on tank pressures of a hypothetical 180-second power loss, after which the backup generators kick on. This is a 24-hour simulation with a hydropneumatic tank, showing initial system pressures at each node. Here we see the tank cycling, and we can also look at the pressure changes over a 24-hour period throughout the system. Using our pressure contours, we can see that this node has the lowest starting pressure due to its elevation and distance from the hydro tank, and since demands are static in this simulation, we know that it will always have the lowest pressure of any node in the system. We can verify this by using the results slider to see node pressures at various simulation times. Therefore, we will select this node, J3, when evaluating whether or not we meet a system pressure requirement of 30 psi throughout the simulation. Looking at the pressure trace for node J3, we see it meets our minimum pressure specification. Next, we can apply an American Water Works Association demand pattern and see the changes in the system. Then we will apply this demand pattern to the residential row. Since we've assigned residential meters to most of the pipes in the system. The simulation starts at midnight, or hour 0 in military time. Demands are low during the overnight hours. Here we see the pressures fluctuating more slowly, since the pump is cycling more slowly. During the morning, and especially the evening hours, the pump is cycling more quickly. However, overall system pressures are maintained above 30 psi. But what would happen if we added more residential meters throughout the system? Residential meters can be seen in the pipe info window. And here is the demand for each residential meter in gallons per minute. Let's say the area's population grows to be 2/3 larger than it is. We will multiply the number of residential meters in each pipe that has them by a factor of 1.66. Then we will reanalyze the system. Looking at the pressure results for node J3, we see that the pump kicks on continuously, approximately between hours 9 and 23. Also, system pressures fall below the minimum requirement. Here is a profile of the system between the reservoir and node J3, showing the hydrotank draining and filling. Other simulations are possible, such as fire flow simulations, and with the optional surge module, users can evaluate the effect of transients on the system. Hydrotanks act as natural buffers by absorbing transient energy, and with the surge module, we can evaluate the degree of protection offered.